We have Rafael Lang of Purdue University. Rafael got his undergraduate degree at the University of Ulm, his graduate degree at the Max Planck Institute in Munich, and was a postdoc at Columbia University and is now at Purdue. And he's going to tell us about the search for dark matter, which is one of the greatest mysteries of mass that we know.
Thank you. Okay, so it's funny you are trapped here when you're standing up here on the podium with a bit of a long wire. Thank you very much for the kind invitation. It's a great pleasure to be here and spend half an hour to talk about dark matter. Wow, that's a big topic. I will be sure to miss out on a lot of details, and you bear with me, please. I want to take a couple of minutes to establish what we know about dark matter and why we know that dark matter actually exists. And to start out, we can start out just a couple of minutes after the Big Bang with Big Bang Nucleosynthesis. We look at that and we find that the more baryons you would have in the universe, the less deuterium we would have, because more deuterium would be fused into helium. So you can measure the deuterium abundance and you find that only 5% of the mass in the universe is made out of baryons. What's the other 95%? You can fast forward 300,000 years after the Big Bang and you look at the cosmic microwave background radiation, and you want to explain those tiny, tiny wiggles that you observe in the spectrum, shown here, for example, from Planck and the South Pole Telescope. And if you want to do that, again, it's not enough to just add baryons, matter that wants to clump, but at the same time feels the photon pressure, the radiation pressure of the cosmic microwave background radiation. But you need to add way more, 5 times more matter that doesn't feel the photon pressure, dark matter yet again. And then you can ask the question, well, our universe is pretty young. It's only 14 billion years old. So how come that those tiny fluctuations evolved into those huge overdensities, stars, planets, you and me, that we observe today? And if you want to do that, you look at structure formation. We can understand it actually pretty well, at least to first, second, and third order. But if you want to understand it, you need to add a lot of dark matter, actually only dark matter in your simulations, and you understand it. So we have evidence for dark matter at all time scales, from the earliest times of the Big Bang all the way to today. It's not only that we have evidence for the universe for dark matter from cosmology, but we also have evidence from astrophysics. For example, you can look at the galaxy clusters. Historically, one of the first evidences came from the Coma cluster. You look at dispersion of those galaxies. They are moving very, very fast. So if you want that to be a bound object, that means the gravitational potential well needs to be very deep to sustain those fast motions. And you find that you need 10 times more mass in those objects than you can observe in baryons. And that includes not only the stars, but also hot X-ray gas, etc. And you can do gravitational lensing studies. You can look at, and you find in those clusters in particular, for example, with this one, Abel 2218, you see even strong lensing. You can see it with the naked eye. Those lenses are so strong you cannot explain that just by the matter that you see. You need to invoke additional dark matter. We can zoom in further to smaller scales. Sorry, before we do that, a cluster merges an interesting study object. I'll come back to that in just a couple of slides. Has been historically very important to disentangle between theories where you say you modify the gravitational law or where you invoke new particles. What happened here is a picture from the Hubble Space Telescope is actually that there were 2 clusters of galaxies that merged in the past. You need to know that most of the mass in a galaxy cluster is not in the form of stars that you see here, but is in the form of hot X-ray gas that you see here. And what you can see is that as the 2 clusters went through each other, and as sketched on the left, the gas got felt some drag, got lagged behind. And okay, now you can again ask your friends from gravitational lensing, say, let's do a weak lensing study on this object. Where is all the mass concentrated? And lo and behold, you find that the mass is not concentrated where all the baryonic mass is, where the cluster is. You can see that by eye, but where the hot X-ray gas is. But it's concentrated where the galaxies are, meaning most of the mass, as the 2 clusters went right through each other, actually just went through and was not impeded at all by that merger. We can zoom in one step further. We can look at galaxies, and probably you all have seen the rotational curves. This is one particular example just because it's very nice and close by, M33 in the local group. What you would expect if you just do Newtonian studies, a gravitational, well, I guess undergrad problem, you find that Kepler motion, you would expect the motion to go like 1 over r squared as you go out. But lo and behold, in this galaxy and every other galaxy that you look at, what you actually observe is that the rotation curve is flat. out to highest radii that we can measure. And what you infer from that, if you just look at the equation, is that you need to have an additional mass component that dominates those objects as well. Needs to go like the M of R needs to go like the radius. And from Astronomy 101, you know, isothermal spheres give you that. This is where that comes out about. So I think as a community, we should get our language straight. Dark matter has been discovered already. We have discovered it at all time scales, and we have discovered it at vast length scales from individual galaxies all the way to the whole universe. The question is not, does dark matter exist? The question is, what is dark matter made out of? And frankly, we have no clue. Depending on how you look at it, you may look at it and say, that's a huge problem. I prefer to look at it and say, that's a huge opportunity that we have as a community. We have this guaranteed mass that is in the universe. We know it's there. It's, I think, actually quite a unique point in history of science, that you know that there is this unknown out there. It's not just that you have this vague feeling of looking up in the night sky and go, oh, what's out there? We know dark matter is there. The question is, what is that all about? And of course, if you are a particle physicist, what you do is you study interactions of this dark matter particle, whatever it is, with all the standard model particles. And if you see it like this, then immediately you see that there is something wrong with this picture. We have all these standard model particles that make up just a couple of % of the matter in the universe. And now I'm really, seriously, should we just add one dark matter particle? Of course, as little as you, I have no idea how many there are, but I think it's much more natural to think of dark matter as a dark sector, as something that is out there waiting for us to discover it, rich with phenomenology and rich in particles. So let's set out and see what we can do very much in the spirit of this Kavli session. And Fred Kavli, I want to give you an overview over the current data that we have. This talk, I couldn't have given that talk 2 months ago there's lots of results that happen so fast, it's really fantastic. Okay, looking first at astrophysics, what can we learn from astrophysics? And yes, we can learn something about the dark matter nature of the particle nature from astrophysics itself. You can, for example, study the structure formulation in detail and see whether you have non-relativistic cold particles, think heavy, or whether you would rather have some warm, hot is excluded, some little bit relativistic particles like neutrinos. There's the question that is still a standing question is the so-called too big to fail problem. You would expect more satellite galaxies in a dark matter halo like that of our own Milky Way, more than we observe in stars. The question is, why did those satellite halos fail to form star formation, produce stars? One way around is to say, okay, you have warm dark matter. It's not quite so easy. Just this January, there was a study where you look at like earlier redshifts, say Z equals Z, and you say, okay, well, we do observe structure back then. If we have warm structure, if we have warm dark matter, then that would delay structure formation. We shouldn't see as much structure in the earlier universe than we actually observe. So there's quite some constraints, and you can actually learn about that. More so, you can even learn, and we are just starting to probe that from galaxy cluster mergers. It's very, very exciting. If you look at the bullet cluster, you can ask the question, well, if this dark matter went through, these huge clouds went through each other, then shouldn't they have been slowed down as well if there's a dark matter interaction? So you can ask, is the center of the galaxies, which is just point particles that go through each other, offset from the center of the lensing that you observe? In the bullet cluster, you don't see an offset, so you derive an upper limit on the cross-section. But you can look at other galaxy mergers. The bullet cluster by now isn't by no means the only one anymore. We have discovered more than 20 other galaxy mergers. And if you look at the discovery chart, we are on an exponentially growing curve here. We're exponentially discovering more and more cluster mergers. This particular one that I'm showing you here is the musket ball cluster. It's a very old one. So if there were a drag that would keep the dark matter back from moving, this cluster would have had more time to spread out the distance between the galaxies and the dark matter. And lo and behold, indeed, you can see that on the left, the weak lensing centroid is offset by a little bit from the galaxy centroid. I think that certainly one of those clusters is not enough to conclude, but I think it shows that there's really exciting particle physics to do with astrophysics, with studying these. A lot of effort is going now into really understanding the systematics. Moving on, just a couple of weeks ago, you may have read it in the news, was quite some signal coming up that points towards sterile neutrinos. Sterile neutrinos, so you add 1, 2, 3 neutrinos to the standard model. You need to produce them somehow in the early universe, depending on how you produce them. They can be warm dark matter, but they can also be cold dark matter. The production, though, usually implies a mixing to standard model in neutrinos, which in turn implies a decay, where decay is in quotes because the lifetime of those particles can easily be 10 to the 16 times the age of the universe. But I show you a diagram which is just one example. You have a sterile neutrino, you mix that with some sterile neutrino mixing angle into a standard model neutrino, and then you can have a charge current loop there, and then any of those two loops loop partners can radiate an X-ray. So since you now have a two-body final state, the energy is just half the mass of the sterile neutrino, so you search for this in X-rays. And just a few weeks back, we have actually seen a line of 3.5 keV in X-rays. This has been seen in 73 clusters of galaxies stacked all together. That is quite important because they all have different redshifts. So if you had an instrumental effect, like we had in the past, at other different energies, you would tend to smear that out by co-adding all those different redshifts. But you can also look at, for example, the persists cluster individually, and you also see this line at about the same energy. You see it with different satellites. 2XMM cameras see it, and the Chandra telescopes see it as well. At a statistical significance of something like 3 sigma, and you see a figure there. The yellow one just gives you an indication of the excess that you have at about 3.5 keV. So where we're just discussing that and all in the seminars, a week later in the Astro Journal clubs, then comes up the next paper by an independent group that actually also sees that same line in Andromeda, in the Andromeda galaxy. Quite amazing, at a similar significance, basically the same energy. What is even more, they also looked at the surface brightness profile in Perseus clusters and find that it falls off just like you would expect from a, say, NFW profile. So it's certainly quite an interesting, intriguing result. What do we do with that? Well, a word of caution, we have seen X-ray lines come and go before, although not at that significance. But it's actually quite intriguing because the parameters are consistent with what you would expect from what you would be allowed from other constraints. And even more intriguing, it is just what you would expect if you want to solve the too big to fail problem with sterile neutrinos. Comes out quite nicely. So I think the mantra here is very clear. We need definitely and urgently more data. These searches have been done with archival data. I'm sure there will be searches with other archival data to look for that line. Astro H is a Japanese satellite, should be going up next year, which will have a much better energy resolution. We will be able to distinguish different production mechanisms of this gamma line, X-ray line. Okay, moving on to another particle, the axion. So the idea there is, okay, you look at the standard model, you find that the effective CP violating term is small, and you say, well, maybe that's small because the axion is a field, and then this gives, because the term is really a field that gives you a particle, the axion. The interaction strength goes like 1 over the mass of the particle. And if the mass of the particle is less than 40 electron volts, then that gives it a stable lifetime at timescales of the age of the universe, so you have a dark matter candidate. And you can search for those particles via the Primakov effect, where you couple the axion to a virtual photon, say, from a strong magnetic field. There's only one real experiment around to search for dark matter axions. There's other axion-like particle searches. That's the ADMX Resonant Cavity Search. So you use big magnetic field. You go down to very, very small temperatures to get the noise level down. What is shown, what I show you here is as you scan the frequency, this is what you would expect to see. This is simulated data if there were an axion. And this tells you already the challenge of this experiment is you need to scan frequency that takes a lot of time. The axion mass can be, over a couple of orders of magnitude anywhere. So you really need to get a very, very high quality microwave cavity so that you can do that in a reasonable amount of time. That said, if this experiment were to come up with something, that would be quite fantastic, because then you can use your microwave oven at home in the kitchen and see whether you find that as well, because then you know where you're looking. The collaboration is proposing to measure most of the expected or a lot of the expected axion parameter space within the next couple of years. And what is shown here is the axion coupling versus axion mass. The diagonal lines is where you would expect axion dark matter to be, and the green and turquoise cyan colored areas are those that will be searched for in the next 1 to 3 years. So we expect results from that very, very quickly. But I want to use this model to just pick out one very nice example of, I think, what is going on in this field, and that was, we just had the discussion in the previous question session about radical new ideas. Here's one of those radical new ideas, and that says, well, if the axion is much, 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 much lighter than what this ADMX can search for, you can actually induce a oscillating electric dipole moment to nucleons, and you can search for that with an NMR instrument, and possibly maybe even with a commercial one. When you match the resonant frequency of the Lama frequency of your NMR to the rest mass of the axion. So it's just a recent proposal that was brought up a couple of years ago, a very new idea. You can, once you have the idea, all you need, of course, is a fancy acronym. So here's the Casper experiment that has been proposed to search for those axions. Just one example. I'm moving on to the big elephant in town, that is certainly thermal relic particles. And I cannot do without showing you what a thermal relic particle is. The idea is, let's invent a particle to explain dark matter that has been, as all the other particles we know, in thermal equilibrium at early times of the Big Bang. So it was constantly produced and annihilated, and so the number density was constant, but then as the universe expands, the temperature drops, and at some point your light standard model particles can no longer produce your heavy dark matter particle, so your dark matter particles continue to annihilate and you drop in their density. That Maxwell-Boltzmann suppression doesn't happen forever, because at some point you have so few dark matter particles left that, depending on their cross-section, they will simply not be able to meet each other anymore, they will not be able to annihilate anymore, and you freeze out at some relic density. And the interesting thing here is that the higher the cross-section, the thermally averaged annihilation cross-section, the lower the relic density that you leave with. That's quite nice if you do, for example, a scattering experiment, because there, of course, you're sensitive to density of dark matter times cross-section, which is basically constant, within a couple of orders of magnitude. So from purely cosmological arguments, has nothing to do with particle physics, you find that the density of thermal relic particles is 10 to the 5 picobarn kilometers per second over the thermally averaged annihilation cross-section. And now you scratch your head, walk across the corridor to your particle physicist friend, and you say, hey, what's your favorite model? And what's your favorite thermally averaged annihilation cross-section? And maybe this guy tells you, well, I would like to have force unification, just one example. Then you write down Fermi's golden rule, and you say, okay, what is that cross-section? What does it come out to? And it comes out to, if you want to achieve unification, you need to have a certain cross-section to make that happen. You find 10 to 6 picobarn kilometers per second. You plug those numbers together, and you say, oh, wow, that gives me a density of 10%. That's about what you expect, what you observe for dark matter in the universe. This is just an order of magnitude estimate, but it is surprising that there's many factors with very, very high orders of magnitude that they actually cancel and come out to give the right thing. So this is why the thermal relic particles are such a popular model. You can search for them in a variety of ways. You can produce them, right, as in the early universe. And you can search for that production in a collider, except that if you look at that effective field diagram that I show you here, you have two standard model particles coming in, two dark matter particles going out. You can't see that at a collider because you can't trigger on that, right? So you need to have something else in that diagram that you can trigger on. But then Feynman diagrams, you can turn them around as you like. So we can turn this around. Of course, the annihilation channel also needs to exist for a thermal relic particle, where you have two dark matter particles annihilating into standard model particles, and you can search for those again in the sky, for example, and we'll be talking about that. But then it's also quite nice when you turn that due to crossing symmetry, you know that for a thermal relic particle, you know that scattering has to be possible as well, and you can search for that in a laboratory experiment. So let's see what we can learn about those weakly interacting massive particles, those thermal relic particles at the LHC. There has been quite a bit of talk about that already. In particular, though, for what concerns dark matter, you can either produce that dark matter particle directly, or you can, Maria mentioned it just previously, you can have a decay of, say, a Higgs boson into those dark matter particles. Either way, the signature is missing transverse energy, and you can search for that quite nicely. I'll just flash very briefly 2 results. Spoiler alert, we haven't seen any indication, any bump, anything yet at the collider searches. Here's an example from Atlas where you look for dark matter production with a mono C or mono W, which then goes in quark-quark. And the top left, you see the spectrum. You have your standard model backgrounds, and you would expect a bump on top of that spectrum, but you don't see that. So you can place limits. You can translate that, again, using effective field theory into limits on the WIMP nucleon cross-section. That was also shown in the previous talk. And what you find is 2 things. Number one, those limits, they go up and down by many, many orders of magnitude depending on which channel you look at and which model you look at. Number 2, those limits are way better than what you can do in direct searches at low masses. So below 10 GeV or so, direct searches they run against their energy threshold. They can't do anything, but really with the LHC that works extremely well. And the third thing you can see is that these technologies are complementary and competitive, probing the same parameter range, which is quite exciting because, of course, we hope to see something in one channel that we would also see in the other. Just another random example, more or less random example, is a monochat final state. You can search for the missing energy spectrum here. The picture is from CMS. And the idea there is, well, if you have those heavy particles, you would expect at some point as you go to high enough energies, you would expect an excess of particles of missing energy, traverse energy events at highest energies due to dark matter. So you can look for those events and you can place your limits. And again, you can place it on those bounds, which are quite impressive, really. There's not only the direct search, there's the indirect searches. So let's look how we can probe those. Last year, the AMS collaboration has located with their detector on the International Space Station confirmed an excess of positrons. Positrons are really nice to look for dark matter because there's not so antiparticles in general are nice to look for indirect searches because there's not so much standard model background. So it's a better signal to background channel to look at. Well, the overall spectrum can be explained quite nicely and quite easily and quite naturally just with some pulsar wind nebula. And for the electrons, you add a supernova. You know those objects are there. You would expect that flux. So really, I mean, yes, it could be a massive dark matter annihilation bump as well. But maybe for the time being, till we learn a bit more as we look at how that spectrum evolves towards higher energies, we can place limits for lower masses. So we can see, do we see additional excesses on top of that positron excess? There's the top left diagram. You see, like, do we observe a line signal due to dark matter annihilation? And you can place quite stringent limits. On particular, for example, just pick one example, you would exclude a thermal relic particle with a mass of less than 200 GeV annihilating into electrons and positrons. That cannot be excluded by that data. Ladies and gentlemen, this next result is from the FERMI gamma ray telescope, and I would consider it, if you ask me for a personal opinion, currently the most exciting signal that we have that could actually be due to dark matter. What you see on the picture is just how the galactic center would look like if you step out tonight and you look at it with your eyes, and you see that little splush there. That's a couple of years ago when Hooper et al. Said, look, in Fermi data, there's this excess of gamma rays, of GeV gamma rays observed in Fermi from the galactic center. That could be due to dark matter. And everybody just said, yeah, look, but it's the galactic center. I mean, there's all kinds of complicated physics, astrophysics going on there. It could be anything, could be millisecond pulsars, whatever. And that is certainly true, except that what happened is that they took this analysis further and they looked whether they can see this excess also at higher galactic longitudes. And really there's not much of a free parameter because you say, okay, if I want this signal to be due to dark matter, you know from your dark matter halo how you would need to extrapolate that to latitudes. And indeed what they observe is that out to galactic latitudes of 10 degrees, and that's what's shown here to scale roughly, out to 10 degrees we pick up a signal that follows just the plain vanilla WIMP scenario that you can imagine. If you have a dark matter particle that goes to annihilates two quarks with a mass of something 10 and 50 GeV depending on the channel, and a cross section somewhere really nicely around the thermal relic cross section, and a profile which is about NFW, then you can explain that signal perfectly. This is a big signal. It's not a small signal. It's about a third in the galactic center of the total gamma ray emission. It's quite exciting. If you want to explain it with astrophysics, you will need some to invent some in astrophysics that scale like an NFW profile squared towards higher radii. So that'll not be very easy to do that. So then, of course, the next thing you say is, well, okay, if you claim that this is dark matter, then let's look at some other dark matter-dominated systems, and let's see whether we see gamma rays from that as well. So let's look at dwarf galaxies, and the FERMI collaboration did that. You see the picture of the dwarf galaxies where they are located, and the Brazil flag block the limit. And I quote from their paper. They say they find no excess that they would report on, so they're placing limits. But they write the most significant excess occurs in the BB bar channel between 10 GeV and 25 GeV. That's exactly where you would expect it from the galactic center. So I think it's really, really exciting here to see what is going on. I'm really curious to see more data from FERMI coming, in particular for this dwarf analysis, seeing whether there's an excess that can be confirmed and what we can learn about that. This is a vanilla WIMP, which would be great because it would also mean it would show up in the direct searches where we probe the interactions with this dark matter particle with quarks. The spectrum, you can easily see that this is just a simple falling exponential. You can do that if you just, okay, the spectrum will be proportional to the flux of particles, which is proportional to the velocity of the particles, which is proportional to the velocity integral of those particles, and you do that in your head and you find it's a simple falling exponential. Except for some form factors, doesn't matter. As you can see from the plot, it actually comes out on a log scale as basically just a flat line. But the maximum recoil energy is very low, so that makes it so challenging. If you have ever worked with a germanium detector in your lab, any detector, any particle detector really at lowest energies shows an exponential increase in noise. Okay, so that's the challenge of those experiments. And if you then look at the snow mass process, then this is the plot you find about the status of the field. For the sake of this talk, please allow me to simplify it. It's a plot of the cross-section versus mass of the particle, and basically this is what is going on. The first thing you should notice is a log-log plot telling you that we are covering vast spaces, but also we don't really know what we're doing, right? We don't really know what dark matter is made out of. There are gray areas which are generically falling into separately discussed often areas where you have the vanilla WIMPs at hundreds or thousands GeV that come out of supersymmetry. There's other scenarios. For example, if you couple it if you relate your dark matter to the asymmetry in the universe, you would maybe find lower masses. And what you see is that the limits that we place today with those detectors, as with all the other detectors I've talked previously, probe the relevant parameter regions. Really, that is the exciting thing about the times that we are in. Our experiments have the sensitivity that they need. You can also see that there's a yellow blob up there with some detections. 4 weeks ago, that would have been still there. By now, I cut the slides out because these detections have been ruled out. Most recently, by the Super CDMS collaboration, they use germanium crystals, have been completely revamped their detector crystals using interleaved electrodes. And they did a first analysis where they targeted precisely those hints of detections at 10 GeV masses or so, and they were looking to see what they can say for that. So they did a targeted analysis for low mass WIMPs. They expected 6 background events, observed 11. Really, it's only 8. So there's no excess there. Excludes the cogent excess. For example, you can see that on the plot by something like an order of magnitude. It's quite a fantastic result, quite striking, came in a couple of weeks ago. Also, what is nice about this paper is something qualitatively new for the field of direct searches. That's the first time, Joe, you mentioned it as well, it's the first time they used a boosted decision tree in any of those analyses. That's at low masses. At high masses in the vanilla WIMP scenario, currently the best limits come from the LUX experiment. Just like the Xenon 100 experiment that has now been surpassed by LUX, it's a liquid xenon time projection chamber. What is really happening here in the field is also, I would call it a revolution. The experiments are getting extremely sensitive, and extremely careful in what they are doing. We have precision calibrations in this example, for example, in situ nuclear recoil calibrations using deuterium neutron generators, in situ calibrations of background using tritium beta decay elements. So that really in those experiments, in those liquid xenon TPCs, we now have the systematics under control to the % level. Keep in mind, we are looking for dark matter on a log-log plot, yet we know what we're doing to the %. It's a fantastic accuracy. Lux has published last fall first limits from a search of about 3 months. They have not seen an excess. What the white data points along the yellow line, that's background. Blue is where the blue lines is where you would expect your signal. You don't see any, so you place a limit. And that makes me coming back to this direct scattering overview. Simplified plot where I want to give you an overview about what will be happening here. The orange line is ruled out. Lux should be expected to give result within a year, going down by about an order of magnitude. We are already now building Xenon 1 ton. We'll fill that detector by the end of the year, containing 3.5 tons of total target mass. We should expect results by 2016, maybe 17, going down 2 orders of magnitude in sensitivity. It's mind-blowing how fast those experiments are moving ahead. We are more than doubling our sensitivity every single year since 20 years already. It's really amazing. Even further than going a factor 1,000 beyond where we are now, probing vast regions of the expected parameter space will be done with the experiments. I just name a few here: LC, Xenon N-ton, or DarkSide G2. Those experiments have been proposed already to the agencies, not in some technical design phase, but actually being proposed. We have the technology to probe that. We have the technology to go all down to the way to this blue region, to a signal of coherent neutrinos, interactions, can be neutrinos from the sun or from the atmosphere, and they would interact with the nuclei just like you would expect from dark matter. So it's a new signal that we can hope for to see in those detectors. So I'm concluding my talk. I hope I was able to convince you, if you weren't already, that dark matter does exist. But we have no clue what it's made out of. So that was premature. There you go. So the fantastic thing is that our experiments today do have the sensitivity that they need to probe our most promising models. Any excess that you see in any of the experiments very reasonably could be due to dark matter. And consequently, we'll scrutinize our most promising models within the durations of 2 PhDs or so. Coming back to the discussion that was mentioned earlier, do we need radical new ideas? Well, if something shows up really and is confirmed those detectors, I mean, fantastic. Look, golden age of dark matter physics, beautiful. If nothing comes up, I think now is about the time to think about alternative theories, and we have a few of them. I think we need more. We should really keep pushing forward. This is really exciting. We have a complementary and leading effort in the United States. There's a fantastic science return on your investment, and you get an amazing amount of science out for any dollar that you put in any of those searches. So it's really money extremely well spent. It's an ideal area to train your students. It's like you get everything from analysis, from theory to hardware. It's just as you want it. That's just the area you want to be in. Thank you very much for your attention.
Hi.
Yes.
Is this on? I'm just wondering if the FERMI results are right, or the Galactic Center is a 30 GeV-ish WIMP, how would that show up in the direct searches? I mean, that's also an area where they are digging down very deep.
Yep. And the answer is we would see that any time. And
any day now, huh?
Yeah. No, absolutely.
But I mean, is there a scenario where you wouldn't see it in the direct searches, and what kind of WIMP would that be?
So if you look at the FERMI data in a bit more detail, you can do different. I mean, there's some uncertainty that comes in from the propagation of cosmic rays in the galaxies, and but you can say model that as a decay to BB bar, for example, and that's actually the best fit scenario. You can also model it to democratic annihilation to any quark. Okay, now why would dark matter annihilate only to BB bar? Okay, now if you invent a model in which dark matter only couples to BB bar, that will greatly reduce. I mean, my detector, my direct detection detector, doesn't have any B's, right? So That would greatly reduce the rate there. At that point, it will depend on the model, but conversely, that means depending on what we see in those different approaches, we will be able to disentangle the different models. I think that's really the great opportunity that we have with this signal.
Please, I apologize if you said about it, but I missed. But I really was surprised by the words warm dark matter. I know, as I remember, I have some memory from my young years that warm means radiative, electromagnetic radiation in particular. That's warm means by definition not dark. What did you mean by warm dark matter?
Okay, so this is just a language. Sorry for the semantics. In the early days when people were studying structure formation, the two models that were most discussed were cold and hot dark matter. And what that really meant is non-relativistic cold dark matter and relativistic hot dark matter. It has nothing to do with the radiation. It's just that, whether you have, whether you have relativistic matter or non-relativistic matter. And hot dark matter, relativistic dark matter was very quickly excluded because of structure formation. It would wash out structure. We would not be able to live in the galaxy we live in today. But then, of course, there were some problems like the too big to fail problem, like at the core cusp problem. And at that point, then, once you look in that detail, you can put in back a little bit of relativistically, like a bit faster matter, and you wouldn't call it hot. You would call it, let's call it warm. And that's where the name comes from. It's really just a lame compromise between hot and cold.
Thank you.